tired?
I got it to the point where
It's almost Friday. So close. Yeah, I don't have anything going on tomorrow, so I have somebody coming out to winterize the sprinkler system.
It's got to blow out.
Exciting, yeah. Super exciting.
I would say, people think the Grayson is in Colorado.
No, I've been here for a while, like 12 years. Yeah. So, are there any questions on the homework? We're still in. Remember, we skipped 4.2 for now. We're still in 4.3. We've kind of barely started 4.3. All right. We'll keep on moving then. I hope that you've had a chance to look at some of the homework, just so that these different things we're talking about aren't like flowing into each other. Because we kind of keep adding to until we get to section 4.4. All right. The last example we left off was with finding or stating the intervals of increasing and decreasing for the function x times e to the negative x. So we find the derivative where the derivative is 0 or undefined, and then we test points or intervals rather to determine where the first derivative is positive and negative. Where the first derivative is positive, the function itself is increasing, and where the first derivative is negative, the function is decreasing. So that particular example, were there any questions on that? I think we'll check out the graph. All right, so we see that the function's increasing until an x value of 1, and then it decreases. You know, there's other tools that we have. For instance, we see that this graph has a horizontal asymptote. So all of those things are still relevant in graphing, and perhaps when we talk about graphing in the next section, these things come up. But that's more of a chapter 3 thing, right? Like, how do we determine the behavior of a function near its vertical asymptote? How do we determine the end behavior of the function? So anyhow, we could find the horizontal asymptote there. Looks like it's at 0. Right? Compute the limit on the given function as x approaches infinity, and then we know where the horizontal asymptote is. So just a reminder on that. Everybody okay with that example then? All right. And like, you know, what we were looking at is with these particular examples, we were describing where a function's increasing or decreasing. And we said, you know, at least right now, there's no way for us to know that a particular critical point does actually correspond to a local minimum or a local maximum. So then the next theorem actually tells us how we can determine if a critical point is a local minimum or a local maximum. As a reminder, what we said was that in general, critical points are only candidates. If you want to know if a specific critical point corresponds to a local min or a local max, then we have to perform the first derivative test. So luckily, we're already doing that, I guess, when we determine where is this function increasing and decreasing. We're already doing this. So if we're determining where a function's increasing and decreasing, you almost get this first derivative test as just a byproduct of that. But what it says is, if the derivative changes sign from positive to negative, then you've got a local maximum at that critical point. If we change signs from negative to positive, then you've got a local minimum at that point. If f is positive or negative on both sides, then there is no local extreme value at c. So like if we're, like on that last example, if we're looking at this interval for our first derivative, and we're testing whatever points we chose. We're testing this point and this point, and we saw that it was positive and negative. We stopped there and said, okay, well, the function's increasing and then it's decreasing. But if the function, if f of x is increasing here and then it's decreasing here, what happens on the function at 1 itself, if that was a critical point where the first derivative was 0? It's what? It's horizontal, right? So it's, we're kind of exaggerating, but the function's increasing and then it's kind of flat right there at that very point, and then it decreases. So you've got, you literally can see this peak that the function has. There's a local maximum at this point. And you've got a similar situation if it were, I don't know, like here's your first derivative. And let's say that's a value of 5. If your first derivative was negative and then positive, then again, what that means about your function f of x is that it's decreasing, it's flat here, and then it's increasing. So again, you can literally see if you draw out what the function's doing, that there is a local minimum there. So that's, the first derivative test is for local mins and local maxes. But it is just a byproduct of testing for intervals where the function's increasing and decreasing. Does anyone have any questions on that? So again, it's not sufficient enough to say I've got a critical point, therefore it is a local minimum or a local maximum. You have to look at the sign of the first derivative. If the first derivative changes sign as you move across a critical point, then there will be a local extreme there. Which one, as we see, depends on if it goes from positive to negative or from negative to positive. Yeah, so the example we used when we said that just because you have a critical point doesn't imply that there's a local minimum was the graph of x cubed, or the function x cubed. So just to illustrate that last bullet point, if we have f of x being x cubed and we look at its derivative, and where the first derivative is 0, we can see that the first derivative is 0 when x is equal to 0. So we would say, all right, well, there's a critical point of the function x cubed, but when we look at its, if we were to look at its sign chart and do this, we would test this value and this value. But both of those values get plugged into the 3x squared. So it doesn't matter that they're positive or negative, right? Because we're squaring them and then multiplying them by 3. So they're going to both be positive, or all values rather are positive. So if you looked at that and said, well, that means the function's always increasing, but it also means that there is no local extreme at an x value of 0 because you didn't change sign. The first derivative didn't change signs. So this is that third bullet where there is no local extreme. Or if they were both negative, it's same result. But if we looked at the graph of x cubed, we also see that as well. So here's the graph of x cubed. There's our critical point. All right. Any questions on any of that? So let's take the intervals of increasing and decreasing and identify any local extremes. Extrema. And I think it's always wise to look at the domain of the function you're given first. So let's go ahead and state the domain of f. Domain of f. Yeah, all real numbers. Do you all agree with that? We just have odd roots. Okay, so we're dealing with a function whose domain is all real numbers. Let's compute the derivative, because remember the intervals of increasing and decreasing and local extreme all come from that sign chart of the first derivative. So we're going to find the first derivative. What would the first derivative be?
Over 3x to the negative 2/3.
Okay. Well, x to the negative, sorry, what did you say?
X to the negative
2/3, okay.
So it'd be x to the negative 1/3, because if you're subtracting 3/3.
Yeah, so remember subtract 1 from the power. 2/3 minus 3/3. Negative x to the negative 1/3, okay. To the 2/3. Okay, so that's the first derivative. Again, what we're looking for is two things at this point. Once you have the first derivative, one, where is the first derivative 0? And two, where is the first derivative undefined? So which one do we want to look at first? Does it matter if y'all have a preference? Well, so, all right, is there an area where the first derivative is undefined, or is it always defined?
Yeah, it's always.
It's always defined? What does a negative exponent mean, though?
Yeah, the x goes in the denominator.
Yeah, the x goes down to the denominator, so anything that makes that denominator 0.
Yeah.
Essentially
So,
just saying
I
x
think it might be more conducive to look at our first derivative for solving when it's 0 as it is, but you just got to be mindful that the first derivative is actually, that first term anyways, is 4 over the cube root of x. And then we have 5/3 times the cube root of x squared. So where is the first derivative undefined? When x is 0. Let's be a little more specific here. F prime of x is undefined at x equals to 0. Certainly within the domain of the original function, which was all real numbers. Okay. And then we have to figure out where does 4/3 x to the negative 1/3 minus 5/3 x to the 2/3 equal to 0. At 0, right, when x is 0, but then we're asking where does this whole thing equal 0? So what is there even an x value we can plug in here and here to make that all 0?
horizontal tangent.
So before we look at that, just like we've noted here, the first derivative is undefined at x equal to 0, but the original function is defined for all x values. So when does a function's derivative not exist? What happens on the function? A couple of things.
Ask that again?
What happens on the function when the function's defined, but the first derivative is not defined. A what? No, that would, a hole is where the function is undefined.
Maybe like a jump discontinuity.
We could have you're right, a jump discontinuity. What else?
Could like not be connected.
Yeah, not connected.
Anything makes it non.
Sharp corner, yeah.
Corner or a vertical tangent. line.
Or a vertical tangent, right? So all of those indicate our visual ways to see where a first derivative is undefined. So just keep that in mind when we actually do look at the graph of the function. The function's defined everywhere, but the first derivative not being defined at 0 is going to tell us that, well, either the slopes get more and more vertical, there's a sharp corner. We know that in this instance, since the function's defined everywhere, that there's not going to be a jump. So we either got the tangent lines becoming more and more vertical, or the tangent lines are meeting up at a corner. So we'll see that once we graph it.
So you can have a discontinuity or because either you have a discontinuity or it can be non-differentiable, right?
Yeah.
Both situations would cater to undefined.
Right.
Continuity and differential. Okay.
Yeah, yep. Yeah, because if your original function's undefined, like, I don't know, if you're, let's just say the function that we're looking at is not defined at an x value of 2. It doesn't make any sense to say, find the slope of the tangent line right there, because there's nothing there, right? So you would see that come through in your, your derivative is also undefined at x equal to 2. Okay, so remember the strategy in general here is when we're solving these kind of equations where we have the first derivative being 0, we just want to factor out the greatest common factor if that's an option. So we can certainly factor out of the constants, we can factor out a 1/3. What can we factor out from the x's?
Next to
X to the, yeah.
The negative 1/3? Hmm.
Could you factor out, would it be positive or negative?
It just matter how you want to change your sign.
So would it be positive or negative 1/3 that we could factor out? I don't think it really matters.
I mean, you just have to change your signs no matter which way you do it.
Right, if you had like x to the 4th minus x to the 5th, right, I could factor out an x, I could factor out an x squared, I could factor out an x cubed. It doesn't matter, I can factor either or out of that and still have a factorization.
X, then make X to the 1/3.
So let's try x to the 1/3
X to the negative 1.
or negative 1/3. Sorry, I don't know if you were just talking to your neighbor or you were suggesting we factor out
No, sorry. I was
1/3.
just-
Okay.
Gotcha.
So generally with these, like we see, all right, well, you take out the smallest one, right? I'm going to take out x to the 4th because there's an x to the 4th here and there's an x to the 4th here, right? So the smallest one here is the negative 1/3. So we'll take out an x to the negative 1/3. And then what are we left with in here?
You have 4 for the first one.
4 is the first term. Minus,
5x.
is it 5x? So it's weird, we're probably not, haven't seen a lot of problems where we had to factor out fractional exponents, but exponents are exponents. They behave like they always behave. Well, so let's just check if we, because I heard negative 1/3 first. 1/3 x to the negative 1/3 times 4 certainly gives us this first term, and 1/3 times 5 gives us our 5/3. But when we multiply x to the negative 1/3 by x, do we get x to the 2/3?
Is it negative 2?
You just want to find two. I'm trying to think of what this is. It's essentially because it's going to be a sum, isn't it?
Yeah, you
Since
add
they're-
the
since they're
exponents.
multiplying, so you're just. You
So-
need to just find
So
whatever
x
negative
to the-
1/3 plus x equals 2/3, and your x is what your exponent's going to be.
Yeah, exactly. So we don't know, there's an x to some power there. Maybe it's to the 0th power, clearly it's not, but there is some x to the power because we're factoring, just like factoring something like this. We don't know we're unsure of what that is, but we know whenever I multiply what I took out by this here, I should get the 2/3. So we could say what number, let's do this. You can just solve it algebraically.
Yeah, so I'm saying just get -1/3.
What number needs to be there so that remember when we multiply the exponents, multiply the x's together, we're going to add their exponents. So this number and this -1/3, they need to combine together to give us 2/3. So what should that number be?
Just 1.
Should be 1, right?
3/3 or 1.
Yeah, 3/3 or 1.
This is why we do fractions.
Yeah, maybe we dislike fractions because of this, but we like algebra because it tells us exactly what it should be. All right, so that's just 4 minus 5x. I'm just going to leave that exponent there for now, just because we have that supporting work below it. All right, now we have two things for our first derivative. You've got two things multiplying, giving us 0. So either 1/3 x to the -1/3 equals 0, or the 4 minus 5x is equal to 0. When does the 1/3 x to the -1/3 equal 0? When x is 0. Again, think of it, let's rewrite it. It's 1 over 3 times the cube root of x, right? So it's not equal to 0 when x is 0. It's actually undefined when x is 0. But when does 1 over 3 times the cube root of x equal 0? It's undefined when x is 0. When is a fraction equal to 0?
When its numerator is equal to 0.
Only when the numerator is 0.
So it never equals 0.
No, it's a solid coefficient in the
Right.
numerator. You can't, there's nothing to change. Won't happen.
That actually never equals to 0. We see that it's undefined at x equal to 0, but we've already found that, right? We already said the first derivative is undefined at 0. So we already knew that it's undefined at 0. So that factor never contributes to our first derivative being 0. And then 4x minus 5 equals 0 when x is 4/5. Let me write it. When x is equal to 4/5. So, I mean, granted, the function that we started off with, it's a weird function, but we have certain tools that'll tell us what's going on. What is it? When is it increasing, decreasing? Is there a maximum or a minimum? And so we've come up with the first derivative is 0 at x equals to 4/5, and the first derivative is undefined when x is 0. So it's a lot of work to get that sometimes, but what do we do now? What's our next step?
You do your line graph and
Yeah.
determine increasing.
So we have the first derivative. 4/5 was a critical point. Just put that here. And the first derivative itself was undefined at 0. So I don't know if you want to indicate that in a specific way. There's usually not an agreed upon thing, but the first derivative doesn't exist there. But remember, the only thing we're using the first derivative here for is to answer a question about the function itself. So there's our two critical points, and then we'll just test the three values here, here, and here.
Negative on both sides.
So -1 maybe for this one.
-1 and 1/2 on the other end.
1/2,
And then 1.
and then 1. So we're gonna evaluate. Remember, you're evaluating your first derivative at those test points. At a derivative representation or its factored representation. We use either one because it's both the first derivative, but we do want to plug those numbers in. So you just want to try to verify that you are coming up with, let's do this here. F prime of -1. You should come up with a negative result. So negative there. F prime of 1/2 should be positive. And F prime of 1, you should get it to come out to be negative for that one. But just kind of over-exaggerate those. And when you describe the intervals of increasing and decreasing, etc., we're kind of chunking that up in terms of the critical points. Just to be careful, because I see sometimes people will write out their test point instead. You're always going up to the critical points, not your actual test values.
I'm just confused why we're including 0 from there.
It's because it's still a critical point. It's where the first derivative was undefined. So,
Oh, yeah, okay.
yeah, you could have some funky things happening on the function even if the first derivative is undefined.
Yeah.
Okay, so once we have this chart, then what do we know? What does this chart tell us about our function? When the first derivative is negative, what is f of x doing? Decreasing. So f of x is decreasing on the interval from -infinity to 0. And I'm just going to do this in red just so we're all on the same page. We're stopping at our critical point. Decreasing from -infinity to 0 and from 4/5 to infinity. Increasing on the interval 0 to 4/5. And what else do we know? Mike?
We've got a local max at 4.
Local max at 4/5. Do y'all agree? Local maximum at x equal to 4/5
And a local minimum at 0.
and a local minimum at 0. So the function itself, just write this here, the function itself is decreasing, it's flat, then it's increasing, then it's decreasing, right?
Can we have a local minimum where it's undefined?
Yeah, can we have a local minimum where it's undefined? So let's be more specific about what do we mean by its. Can we have a local minimum where the first derivative is undefined?
Yes.
Yes.
Because it's only the first derivative that's there, because
Yes.
the graph goes like this at that point, and so the graph is defined there, but the derivative isn't because it goes like that.
Right, remember the domain of the function that we're describing is all real numbers. Our function isn't undefined anywhere, but our first derivative is undefined at 0. But again, what that meant for us is that either on the graph of f of x is our slopes are getting more and more horizontal, or we have this sharp corner, or this cusp. So you can have a local minimum where your first derivative is undefined. You can have local extrema where your first derivative is undefined. You just can't have extreme values where the original function is undefined, because there's nothing there. All right, so we see the change in sign of the first derivative from negative to positive means that we have a local minimum. At x equals to 0, and a local maximum, say local, at x equals to 4/5. So in this instance, both of our critical points were actually local extrema. That's not always the case. It just depends on the sign as you move through the derivative.
And when writing the local min and max, do we ever have to like find the y value of it, or are we only ever say what it's at?
Yeah, so sometimes, I think, especially when you're graphing these things, it makes more sense to determine the point in which your function has a local minimum or a local maximum, not just what x value it has.
So we just plug those back into the original function to get it that way?
Yeah, into the original function. Because, again, all of this first derivative stuff here is merely to answer questions about the function. Once we know the location the original function has a minimum or a maximum, to get the minimum or maximum y value, we plug that back into f of x. So let's just say here, a local min at x equals to 0, that is, at the point zero comma f of 0. And our function at 0 is 0, so we have the point 0, 0 as the local minimum. I'll just highlight this here. The local maximum when x is 4/5, that is at the point 4/5 f of 4/5. So that was 2 times 4/5 to the 2/3 minus 4/5 to the 5/3, which is it's not an exact value. So we'll just say at 4/5, and that's approximately 1.034 is the function's local maximum. So yeah, anytime you need to find a point, and that's why I recommend just starting these things, because not only are we going to do this stuff with the first derivative, but we do almost an identical thing with the second derivative that tells us a different piece of information about the function. So you've got like your first derivatives hanging out, your second derivatives hanging out, you're plugging stuff into the first derivative, the second derivative, and then eventually you need to plug stuff back into the original function. So it's super helpful to be able, or to be aware of what you have to plug in where to get the specified information. Okay, so any questions on what we've done so far? We're done with that. We've given all of the information it's asked for. But are there any questions on that? It's a really lengthy process, right? That's why most people just use computers to do all this. So let's look at the graph and see kind of, what's happening, especially at 0, where we said the first derivative was undefined, but the function still exists there. All right, so there's the function. See here. Notice if we're back here, it does kind of look like a drastic corner, right? But when we get closer and closer to that, we can see that it's more gradual. So it's not that there's a sharp corner here, it's that we have a horizontal tangent. A vertical tangent, thank you. So the tangent lines are just getting more and more vertical as we go down. Again, just imagine your pencil's like sliding down the function, right? The pencil's going to get more and more vertical as we approach the origin. So vertical tangent there, but we see the function's decreasing until that point, then it increases into 4/5, and then after 4/5 it decreases. But also that we've got a local minimum at 0, 0, and a local maximum at 4/5, comma, f of 4/5. Any questions at all on that example? This example will lead us into the next theorem, but notice here this we only had a single local minimum and a single local maximum. Like if you were to look at a polynomial, that's probably not the case. Like some polynomial that's doing something like this. Well, I should do more, but you know, in general, those things could have more than one local minimum or maximum. Like something like that. We have two local maximums and two local minimums. It really just depends on the function. But the next theorem tells us that if we have one local extreme, we know that that is the absolute extreme. So if we've got one local minimum, that's the absolute minimum. If we only have, and this is either or, it's not both, right? So only one local extreme implies absolute extreme. If there's only one local minimum, then that is the absolute minimum. If there's only one local maximum, then that's the absolute maximum. Notice that wouldn't exactly apply to the function that we looked at, right? We wouldn't say that there was one local max and one local min, so we've got an absolute max and an absolute min. It doesn't work when there's both. It's just a single one at a time, and only one. So just a quick example, and then we'll look at x to the x. But the function y equals x squared is a very straightforward example to reinforce that. We have one local minimum, no local maximum, right? Just one local minimum. Therefore, that local minimum is also the absolute minimum. Yeah.
And that's like, so if we're not restricting the domain, obviously it goes on forever, so the infinities don't count as maximums.
Right, exactly. Yeah, what do we need to have both an absolute max and an absolute min?
A restricted domain.
The function restricted on a closed interval, and the function has to be continuous. Yeah. So there's no way this theorem can guarantee both, because it's very general. It just says suppose the function's continuous on an interval. It doesn't say anything about that interval, right? If it says suppose a function's continuous on a closed interval, then this theorem would guarantee both, but there's no way to do that, so that's why the theorem doesn't say that. So in this previous example that we did, it's true that it only had one local minimum and one local maximum, but is that the absolute minimum? Clearly not. There's more values down here. That's not the absolute minimum either, because there's more values up here. All right, so then let's show that f of x equals x to the x. has an absolute extreme on its domain. So what is the domain for the function x to the x power? Could we include negative numbers? Like, what is negative 1/2 to the negative 1/2? That's an imaginary number, right? What's one way to look at this function, or what's the way we've looked at this function? As what?
As an absolute.
Not as an absolute value. A function raised to another function, yeah. So how do we rearrange those or rewrite those? Yeah.
Any logarithmic way.
Do you remember this
Yeah.
property? What is it? E to the natural log of x equals to x.
Yes.
Okay. So doesn't x to the x equal e to the natural log of x to the x? Remember that? Our old friends coming back. It won't go away. So to answer the question about the domain of x to the x, let's rewrite f of x, x to the x, as e to the x ln of x. So then, what's the domain of f? Is there any issues with e? It's exponential. Is there any issues with x? Not with the first one, but the same x is here inside the logarithm. So what's the restriction there? All positive numbers. Domain is 0 to infinity. That's simply coming from the logarithm, or the natural logarithm, but. Okay, so this thing says, show that x to the x has a local extreme, either a minimum or a maximum, or sorry, an absolute extreme rather, absolute min or absolute max on its domain 0 to infinity. So notice this is unlike what we looked at in 4.1, where it said, determine the absolute max and min of this function on this closed interval. We had to find the critical points, and then we plugged the endpoints into the function. We can't do that here. It's not on a closed interval. Part of that process is still the same, though. If we look for the critical points, we can try to see what those do for us. But there's no way we can plug in our endpoints. So to find an absolute extreme, let's see what the first derivative process tells us. What is the first derivative for x to the x? Since we have it rewritten as e to that power, we're going to say that it's simpler to take the derivative of e to the power as e to the power times the derivative of the power. What's the other way we could use to find the first derivative? There's another technique we could use. Yeah, the logarithmic differentiation, right? Okay, so we have e to the x ln of x. And then the derivative of x times the natural log of x is a what rule? a product rule, product of two functions of x, x times the natural log of x. So we have the first times the derivative of the second, x times 1 over x, plus the second times the derivative of the first. Let me just do this here. Which one? So it's the second, which is natural log of x, times the derivative of the first, so times derivative of x. 1, yeah, so ln times 1 for that one. Or if you like, we don't have to, but e to the x ln of x is x to the x. I think it probably makes a little more sense to leave it as e to the x ln of x, because remember, in order to find the critical points, we have to determine where the first derivative is undefined and where it's 0. Okay, so there's the first derivative. Where does the first derivative equal 0? And where is the first derivative undefined? Is our first derivative undefined anywhere? At 0, yeah, because you can't take the natural log of 0. Where else? And negative numbers, right? So we're looking at our first derivative, we still have that ln hanging out in our first derivative. We wouldn't be able to use any negative numbers or 0, but the original functions domain was from 0 to infinity. So those aren't even considered. And what we're really asking is there anywhere in the domain of f, is f undefined, f of x, sorry, is f prime of x undefined anywhere in the domain of the original function?
Technically, no.
Technically, no. That is, the first derivative is always defined on that domain. Where's the first derivative? 0. So we've already got it factored. When does e to the x ln x equal 0?
I don't think it can, does it?
It doesn't, right? It's an exponential. Exponential functions are never 0. It's by themselves. Exponential functions by themselves are never 0. That's sufficient. So that factor is never 0. When does 1 plus the natural log of x equal 0?
0, 6, 7.
Does not exist?
Yeah.
I heard that.
We could do,
So when does the natural log of x equal -1? Can it? We can't evaluate logarithms in negative numbers, but do logarithms output negative numbers?
Yeah.
it'll just be e to the -1.
Right.
Would be the unsimplified answer.
Logarithms output all negative numbers, but it's only for positive inputs that they output the negative numbers, right? Specifically, positive inputs that are in between 1 and 0.
So instead of just being x equals e to the negative.
Exactly, yeah. So when does ln of x equal to -1? That's when we exponentiate both sides, or just rewrite this by the definition of the logarithm. The base e to the -1 equals x, however you see that. I'm not sure what 1 over e is, but it's certainly positive. Okay, if f prime wasn't undefined anywhere. It's 0 only when x is e to the negative 1. So what we're trying to do now is to show, or to determine, is that critical point actually corresponding to a minimum or a maximum? So then we have to look at the sign of the derivative. Does it change as we move through that e to the negative 1? So when we look at the first derivative, remember the function's domain was from 0 to infinity. So you don't want to make the mistake of drawing the first derivative out like this, because the first derivative isn't, or the function rather, isn't defined on all real numbers. It's only defined from 0 to infinity. And we have e to the negative 1, somewhere here. We've got to choose 2 test values. So what kind of values do we want to choose? Keep in mind that we have to plug this back into the derivative, and the derivative involves a natural logarithm.
You want to do like a negative 0, or I'm sorry, like a 0.2,
Okay.
which would be to the left of e to the negative 1.
And then some number out here, right? Like 5 or whatever?
Yeah, maybe like 0.5 or 0.6 or
Yeah.
larger, whatever you want.
I suppose it's a moot point what actual values you choose. If you're using your calculator, you're just going to plug those values into the derivative. But if you're just gonna look at them and glance at it and say, all right, this is going to be positive or negative, I think it's more conducive to choose e to powers as the value you're plugging back into your derivative. So we could choose what's to the left of e to the negative 1. E to the negative 2. And what's to the right of e to the negative 1? E to the 1. So those 2 values would be, in theory, a lot easier to evaluate the first derivative at. So we're going to do f prime. We'll just do this on top. So f prime of e to the negative 2 and f prime of e. So remember that f prime was e to the x times the natural log of x times 1 plus the natural log of x. We can greatly simplify this process too, because if I compute e to any power, is it ever going to be negative? No, this factor right here, regardless of what you plug in, is always positive. So then we just have to answer the question, what is 1 plus the natural log of e to the negative 2? Is that positive or negative? It's negative, because what's the natural log of e to the negative 2? Negative 2 plus 1 is negative 1. So this factor is negative, and you've got a negative times a positive, which gives you a negative. So this is negative here. If you're using your calculator, that's fine too, but I think it's quicker to just look at this and say that factor is always positive. What's 1 plus e to the natural log of e? Is that going to be positive or negative? Positive. And since this factor here is always positive, this is going to be positive. I'll plug that in, but just want you to see that using your calculator might not be the most efficient way to do these, but if you need to do it, that's fine. So we have e to the e times the natural log of e times 1 plus the natural log of e. And again, that's positive. So f prime from 0 to infinity is negative, then it's positive. And what does that mean?
Local minimum.
Yeah. So I'll just write it back down here. Oops. prime is negative and then positive, right? That means our function is decreasing and then increasing. So f of x is decreasing and then increasing. So that tells us that e to the negative, or sorry, at the x value of e to the negative 1, the function f of x does have a local minimum. So we'll say f of x has a, let's just be a little more specific. F of x has one local minimum. So then by whatever this theorem 4.5, was that right? I don't want to reference the wrong thing. Theorem 4.9. So by theorem 4.9, f of x has an absolute max. At the same location. We should have specified the location, but that's the idea behind that. We can utilize that theorem. We know there's a one local minimum. It has to correspond to the, sorry, an absolute minimum. My bad. The single local minimum has to correspond to an absolute minimum. At e to the negative 1. Okay. Let me just graph that function here. So there's x to the x. Just so we're aware, that's e to the x times the natural log of x. So see, those two functions are identical. There's our local minimum at e to the negative 1. Or 0.368. That local minimum, since it was the only local, it's the only absolute. Anybody have any questions on that? So it's like the derivatives are still present. Mainly, this is f of x. Mainly the process is what we want to be familiar with, because I guess in theory we should know the derivatives. Does anybody have any questions on the process? All right, so let's take a break. We're going to look at the second derivative stuff as well. It's almost identical to the first derivative stuff, except for it just tells you something different about the function.
I can play some things from now.
Okay, moving on. The topic that we're discussing with with concavity and inflection points, we'll connect here, but the definition says we've got a function that's differentiable on an interval. It says if f prime is increasing on the interval, then the function is concave up. If f prime is decreasing, then f is concave down. A change in concavity is an inflection point. So if f changes concavity at some value x, say call c, then you have an inflection point. Just like the first derivative, when you change signs in the first derivative, tells you that you have a minimum, a local minimum or a local maximum. The change in sign here indicates that the function is changing concavity. And so here's a figure to illustrate concavity. Concave up from negative pi to 0, and then concave down from 0 to pi. So you'll notice here the way the concavity is initially defined is it says if the first derivative is increasing. So you got to think of the first derivative as a function. And how do we test whether a function's increasing or decreasing? We have to look at the
Second derivative.
right. So like a function is increasing or decreasing. All those examples we looked at the first derivative. So the first derivative told us if the function is increasing or decreasing. But the way this is defined is it says, is the first derivative increasing or decreasing? So we have to look at the derivative of the first derivative or the second derivative. Right. So that kind of scheme is all the way down with however many derivatives you look at. So if I want to know where the first derivative is increasing or decreasing, then I have to look at the second derivative. And if the second derivative is positive and negative, let's say, then what that means is that the first derivative is increasing and then decreasing, right? So I mean, visually and functional wise, there is a difference. But what we were doing is we were saying that we want to know where the function itself is increasing and decreasing. So what we had to do was look at the sign of the first derivative. And we said if the first derivative is positive, then the function itself was increasing. Negative means the function's decreasing. So it's always that nesting effect that you get with increasing. If I want to know where the fourth derivative is increasing, what do I have to look at? The fifth derivative, right. If I want to know where the 12th derivative is increasing or decreasing, I have to look at the sign chart for the 13th derivative. So the way we define concavity is where the first derivative is increasing or decreasing, which means we have to look at the second derivative. So this is kind of the feature that we have. If the second derivative is positive and negative, what that means about the first derivative is that it's increasing and decreasing. But what that means about, so it's like we're working this way. What that means about the function itself is that the function is concave up. I'll just abbreviate, concave up, and then concave down. So again, we see that here with these red lines indicating the slope or the derivative. So the derivative here is decreasing, the derivative here is decreasing. It starts out really steep rather, the slope is really steep, and then it gets flat to 0, and then it starts to get negative. So that through that whole thing, the slope of that curve is decreasing. On the right here, the slopes are increasing. Or the red lines, the slope of those are increasing. So sometimes the concavity can be like really subtle in how it kind of bends. But just use this as an example, like something that's concave up, you just want to think about like if from the top of the graph, if you were to pour liquid, that the concave up portion would actually hold the liquid, the concave down portion wouldn't. All right, so then the test for concavity then is just like we said, we look at the second derivative. So if the second derivative is positive, then the original function f is concave up, and if the second derivative is negative, your function is concave down. So this is an identical process that we used for the first derivative to determine intervals of increasing and decreasing. We're going to do the very same thing to test for concavity, but our test involves the second derivative instead of the first. Okay. So just like we had in the first derivative setting, where the second derivative is 0 or undefined may be an inflection point. It may not be. Just like where the first derivative is 0 or undefined, it may correspond to a local minimum or a local maximum. And where the second derivative is undefined, could also be an inflection point. Just like where the first derivative was undefined, that in that fractional exponent example, could correspond to a local minimum. So we have a similar kind of scenario with the first and second derivatives, but again, they're just describing different things about the function.
And the inflection point is the concavity.
Inflection point is where concavity changes from like positive to negative, or sorry, where the second derivative changes sign from positive to negative or negative to positive. Yeah. So I think just to see how that all plays out, it's best to just look at an example. So state the intervals of concavity and identify any inflection points. And when we get to 4.4, we're going to graph functions based on what we already know and how to graph them, like what's the domain, what are the x and y intercepts, what's the end behavior, that kind of stuff. But we're also going to use the first derivative and the second derivative stuff to tell us exactly how it bends. So the intervals of concavity and inflection points, we need to look at the second derivative for the inverse sine of x on the open interval from -1 to 1. So if this problem said identify the minimum, the intervals of increasing and decreasing, and where this function has a local minimum or a local maximum, that's the first derivative. Concavity, second derivative. So what's the first derivative of inverse sine?
One over the square root of 1 minus x squared.
Yep, that's it.
1 over root 1 minus x squared.
Oh, these are the inverse ones.
Yeah, the inverse trace.
I read that wrong.
Okay, first derivative, second derivative. I think maybe we could use the first derivative alternate version and say that the first derivative is 1 minus x squared to the -1/2, or you could just use the quotient rule on what we had originally. So the second derivative, chain rule or quotient rule, whichever one you prefer. But it's -1/2 times 1 minus x squared to the negative, we have -1/2 minus 2/2 times what?
-2x.
Yeah, times the derivative of the inner function. Oops. Which I'll just write here. So the second derivative, let's multiply the -2x by the -1/2, so we just get x. Times 1 minus x squared to the -3/2. Or x over the square root of 1 minus x squared cubed. Yeah. So there's the second derivative. We're going to go through the same exact process with the second derivative that we just did with the first. Where does the second derivative equal 0 on the domain of the function? And is the second derivative undefined on the domain? So where is the second derivative undefined? -1 and 1, are those included as critical points of the second derivative? No. So let's just say this, the second derivative is undefined at x equal 1 and x equal -1, but neither one of those are in the domain of the function. So those aren't values we're concerned with. They don't call the zeros and undefined second derivative x values. They don't call those critical points. Critical points are solely reserved for the first derivative. I've seen different labels for this. So I wouldn't call them critical points. Just where we'll just say this, the second derivative is a 0 or undefined. Okay, also now then, where does the second derivative equal 0? Right. So again, the second derivative is just this fraction 0 when the top is 0. So we only end up with one x value for the second derivative test, if you will.
With x equals 0, when we make the bottom of the function undefined as well.
No, because then we would just have, we would have on the bottom the cube root, the square root of 1 cubed on the bottom if x were 0.
Yeah, never mind.
All right, so we do the same thing except for this is the second derivative on the domain of the original function from -1 to 1. And this value, the single value we came up with was at 0. So again, we're just going to pick two test points here. I don't know, whatever, 1/2 and -1/2 maybe. And we're evaluating the second derivative now at those two test values. Oops. So we can just run through this one, I guess. We have x over the square root of 1 minus x squared cubed. So can we evaluate that pretty quickly? Yeah. Does the square root of anything ever output something negative?
Nope.
No. So the bottom, since it's a square root, the bottom always outputs a positive number, right? It's not the negative square root. The bottom's always positive. So really the sign of the second derivative is determined by the numerator, because this is positive, right? So we have a negative over a positive, which is a negative. So the second derivative is negative in that interval. Same thing when we plug in a half. The top is positive, the bottom is always positive. So we just get something that's positive here.
So on the test, is that going to be how you're gonna have questions set up like this. Find the second derivative and draw this little
Mm-hmm, yeah,
thingy.
Yeah.
I don't- Whatever you want to call it.
yeah.
Yeah.
Always have to draw the little thingy.
Yeah. That's part of class.
All right, so what does that mean? I'm gonna rewrite this down here. What we have the test line here for the second derivative that was negative and then positive.
Are those arrows or?
No, they're parentheses from -1 to 1 as the domain of the original function, yeah. Yeah, so if you forgot to do that, then you would say, oh, hey, the function is concave down from -infinity to 0, but that's not true because the function's not defined out there. So you do want to, when you test the first and second derivatives with the number line here, you do want to draw them out according to the domain of the given function. Because anything outside of the domain of the given function doesn't make sense. There's nothing there. And so what that means, you can draw it as a chart, but I would rather you like list it out. This is what's happening. So the function itself, f of x from -1 to 1. Since the second derivative is negative, on that interval, the function itself is concave down. And on the interval from 0 to 1, the function is concave up.
And what does it mean when you say concave down, concave up?
So concavity is, just think of it as the shape of the graph. Something like this, it's a little bit drastic, but something like this or something like that is concave down. And something like this or something like this is concave up.
So is that 0 is the point of inflection?
Yes, exactly. Right, and since we changed concavity moving through 0, or since the second derivative changes sign through 0, that's the point of inflection, where concavity changes, is the definition of the inflection point. So we'll just summarize that here. F of x is concave up on the interval from 0 to 1. F of x is concave down on -1 to 0. And f of x has an inflection point at x equals to 0. It's an inflection point, so we should describe it as a point. Inflection point at x equal to 0, that is at the point, I'll just write this here, 0, comma, inverse sine of 0. Again, we're describing a point on the original function. We want to plug that x value back into the original function. What's the inverse sine of 0? 0. In other words, the sine of what gives me 0? The sine of 0 is 0. So there's a point of inflection at the origin. But that's kind of our summary there. So then, looking at a graph like this, where especially the curvature is rather gradual, it's a lot of times it's impossible to just look at a graph and say, oh yeah, it's concave up here and it's concave down there. Specifically, we could say like around this area looks concave down, but when does it actually change from being concave down to being concave up? Is it here? You know, is it there? Like, you can't tell that from a graph, which is why we have this process. So any questions on that example? Hopefully you can see this perfectly parallels the first derivative test. We're just describing different information. Everybody okay with that?
So does the point of inflection have a slope of 1 all the time?
Not necessarily. It really just depends on the function.
Okay.
Yeah. So the last thing we're going to talk about then is using the second derivative to test for local minimums or local maximums. And this in practice is probably not utilized all that often, but in the problems where you have to find intervals of increasing, decreasing, and concavity, you have everything you need to compute this or to run through this test. So it is an option. It's always an option. It may or may not yield any fruit, but it's always something you can do. Again, in practice, I don't know how often someone would use it. But what it says is that we've got a second derivative that's continuous on an interval containing c, with c being plugged into the first derivative, giving us 0. So with just that statement, what would we classify c as? It's a critical point, because if I plug c into the first derivative, it gives me 0. So c is a critical point. Remember, critical points only come from the first derivative. Okay, so we have that happening, and it says if the second derivative is positive at c, in other words, if we take that critical point and plug it into the second derivative, and that's positive, then f has a local maximum at c. It says figure 440a. We don't actually have that. We can go ahead and draw something to the effect. So first of all, the underlying assumption here is that one of them is that the first derivative at c is 0. So if the first derivative at c is equal to 0, what does that mean about the function around c or at c? Yeah, it's horizontal, right? So there's a horizontal tangent line here. So the function is horizontal there, but the second derivative at that point is positive. When the second derivative is positive, what does that mean about concavity? It's concave up. But we know it's flat right here. Okay, so then it's concave up there around C, but it's also flat at C. So that has to be a local minimum there. It has to be a valley. So that's kind of what figure 440a would show. Also, if the second derivative is negative at the critical point of the first derivative, then you've got a local maximum. So just to reverse the situation here for 440b. Again, the first derivative at c is 0, so it's flat there. But the second derivative being negative means that the function is concave down. at that point. So you've got a local maximum. And often, why we don't use this is the third condition. Because if the second derivative evaluated at the critical point or points of the first derivative is identical to 0, then this particular test is inconclusive. So this test, if that particular thing is 0, it doesn't tell you anything. So it says f may have a local max or a local min, or neither at C. So if we do run into this situation where it's inconclusive, how could we be sure? Like if this told us no information, if this second derivative test told us no information, what could we do?
Just go back to the first derivative.
Yeah, go back to the first derivative. So if it's inconclusive, go back to f prime of x. And what we mean by that is we just look at this thing for f prime. Like what's it doing here and here? And that will tell you for sure. So I think that's probably why it's not used all that much. The benefit is if you can get information out of it, you don't really have to, you still have to find the derivative where it's 0, but you don't have to, you may or may not have to draw out the chart for the first derivative if you're just looking for a maximum or a minimum. But if you're finding intervals of increasing and decreasing, you're already drawing out the number line for the first derivative, so you just might as well use that to determine if you've got a local min or a local max. So are there any questions on that? All right, so then we'll end 4.3 with that. In 4.4, we just put the techniques that we already know in generating graphs. We put that together with the techniques from 4.1 and 4.3. So honestly, in theory, the only new stuff for helping us graph things a little bit more accurately, the new stuff is the stuff we just looked at, the intervals of increasing and decreasing, the local extremes, and the intervals of concavity. And so when we put the first derivative and second derivative information together, really what it generates for us is one of the 4 situations. On a particular interval, is the function increasing concave up, or is it decreasing in concave up? Or is it increasing concave down, or decreasing in concave down? So really, if you think about it, you put the first and second derivative information together, that's what it's going to give you, increasing, decreasing, and concavity. And you have, they're sort of maybe overemphasized for a lot of functions, but this is the main idea. When you have something that's increasing in concave up, you have a shape that's somewhat like that, increasing concave down, etc. So just imagine when we look at the first and second derivatives, if you have like a picture of your function like this, here's a critical point, here's a critical point. Like if you have a picture of your function that it's like increasing in concave down, and then it's increasing in concave up, and then it's decreasing in concave down, you sort of just stitch those pieces together to give you an idea of how the function is shaped. Along with the end behavior, the x and y intercepts, the whatever behavior in your asymptotes if it's appropriate, but all of that stuff technically we've already done. So we'll look at, since we're falling a little behind, we'll look at one example with a rational function for sure, and then if we have, if it's not too much, if we're not too much behind, we can look at like a polynomial or something. So let me just illustrate this. I don't know, if you're using like a graphing calculator, you probably get a similar result if you were to graph certain types of functions. So let's just look at this graph really quick. We're going to look at x cubed over 3 minus 400x. So, I mean, it's sort of misleading in the sense that if we plot it on this, one-to-one aspect here, it just looks like a straight line. But we know this polynomial, it's a cubic polynomial. So it's bending or curving at least twice, right? The polynomials have at most n minus 1 turning points where your degree is n. So a cubic polynomial will have, depending on the n behavior, can have at most 2 turning points. So it looks like this or whatever it looks like, right? Some cubic polynomial is going to have that shape to it. But we don't really see that until we zoom way out on a different aspect ratio. Because if we keep zooming out, oh hey, now we have 3 lines. Now it's 1 line again.
You can see the little indent at 5,000.
Yeah, right. So then you say, oh hey, there's a curve right there. But anyhow, it's not always. Oops. Just scale that, and then we see that it's actually. So, what we're after is how does this curve, like it's concave down, and then it's concave up, and then it's concave down. Clearly those are the local minimums and local maximums, which would come out in the first derivative test. The change of concavity would come out in the second derivative test. Maybe it changes concavity there, I don't know. But that's kind of the idea. If we were to graph that with all of the techniques we have, then we would say, here, here, and here. We would come up with a picture that the function's like doing this, and then it's doing this, and then whatever else it's doing, this, and then this. So you kind of like you stitch those all together, and there's a local max here, there's a local min here. So it's a little bit more accurate than just like an algebra approach where you said, what's the end behavior? I put my arrows here and here. What are the zeros? I have to factor this, right? Typically that's like synthetic division. What happens at each zero? Does it cross or does it pass through, or does it bounce or does it pass through? And then hope, you just got somewhat close to where it turned. That was like the best you could do. So with this first and second derivative stuff, we're just getting a little bit more accuracy in our graphs. And it is a lot of work just for a little more accuracy. So it's kind of, I don't know.
Rough trade-off.
Yeah. This is how it'll be structured on the exam. I'll say graph this function, identify all of this stuff so you know what to identify, but I'll give you the first and the second derivative so you don't have to calculate those individually, and hopefully that'll make the problem a little bit more, I don't know, what's the word? Expeditious. All right, so we're going to graph this function given the first and the second derivative. One thing we should mention that the textbook or the guidelines from the text do have a couple of things that I'm not going to be really particular about. So this is in your textbook or the slides if you want to look at it, but identify the domain. That's really always what you should look at when you graph a function or work with a function. Where is the function defined? But specifically the exploit symmetry part, I'm not going to test you on that. You should know how to find symmetry though, even functions and odd functions. Even functions are the ones that are symmetric with respect to the y-axis, and the odd functions are symmetric with the origin. So that's how you test for even and odd. And, you know, again, based on all the work we're doing, we're just going to stitch it together anyways. So I really don't think that symmetry is doing us a lot of favors as far as the graph. If you know that it's symmetric, then you could probably draw a prettier graph. That's about it. But first and second derivatives, inflection points, intervals of increasing and decreasing, concavity, extreme values, again, all of that stuff, all of those things mentioned in the guidelines from 3 to 4, 5, and 6, that's all the first and second derivative stuff that we've just done. Asymptotes are in behavior, so locate any vertical and horizontal asymptotes and x and y intercepts. So let's first start off with the domain of f of x. So we're just going to go through this process like we would if it were like an algebra class or a pre-calculus class. What's the domain of f of x?
All real numbers excluding 1.
Excluding,
1 and negative 1.
yeah, excluding 1 and negative 1. We are going to have to stop at like 3 because we have a visitor from the academic ASC coming in. I can't see to talk about. Yeah, try to say that. Like it's hard to say.
Academic success center.
Just like that?
Yeah, just like but yeah, we'll have to stop a little early. Say it 10 times fast. So x can't be 1 or negative 1. And just recall here when, just from an algebraic lens, right? If something were to cancel here, what happens? You have a hole in the graph. So if you forgot that, then you find the hole like we found in chapter 2. When you compute the limit as x approaches 1, you see that factor dropping out anyways. So one way or the other, if you've got a hole in there or a removable discontinuity, you should be able to determine that, whether preferably by limits. That's how we should justify them now. But you can see that just algebraically when something cancels. Nothing cancels here, which means that when x is 1 and negative 1, what happens on the graph? Vertical asymptote, right? So I guess that's the second part. What we see then is our domain. It's undefined at 1 and negative 1, but both x equal 1 and x equal negative 1 are asymptotes. So we'll just label this as a vertical asymptote, vertical asymptote. So how does our function behave near the asymptotes? How do we answer that question? In a calculus way.
Limits at infinity.
Yeah, limits. Limits at infinity. So limits at infinity tell us what? End behavior. Limits at infinity when x approaches infinity is for the horizontal asymptotes or the end behavior.
We want the limit as x approaches these values.
We want the limit as x approaches 1 and negative 1. But there's an asymptote there, right? We can't compute a two-sided limit. We have to look at it from both directions. So really, you got 2 vertical asymptotes. You have 4 limits you have to look at. So what's the limit as x approaches 1 from the right? And what's the limit as x approaches 1 from the left on f of x, whatever that was, x minus 1, x plus 1. Should I remember those?
Can we also set the first derivative equal to 0 and I'm sorry. Wait, my brain has stopped. I'll figure it out.
All right, fair enough. So as x approaches 1, the numerator 3x approaches 3. What does the denominator approach?
Let's see. That's positive 0.
0. This factor approaches 0. Well, let's look at it because it's this factor times this factor, right? The x plus 1 factor just approaches 2. So that's 2 times this factor that's approaching 0, but we always had to answer the question, we're approaching 0 on that particular piece through positive or negative values. They're positive, right? Because we're to the right of 1, that means those numbers are slightly larger than 1. And when you subtract numbers slightly larger than 1, when you subtract those from 1, you get a really small positive number. So however you want to indicate that, I know some people were just writing SP, LP for small positive, large positive, that's fine too. But we have to take in the entire quotient. The fact that the denominator is approaching 0 tells us that our answer is infinity, right? But the sign of the infinity is determined by what we have here in the quotient. We've got a positive divided by a positive, so this thing will approach positive infinity as we approach 1 from the right. So do I remember doing all this? All right, as we approach 1 from the left, is it negative infinity? Numbers, again, this top is 3 and this second factor is 2. So those are both positive. Numbers smaller than 1 here,
Is it negative?
they're negative, right?
It's a number that's really, really close to 1, but it's like 0.9999
Yeah.
minus 1, which gives you a really small negative number.
Right. So like to the left of 1 are numbers like 0.9, 0.99. All of those minus 1 are negative. So we still have this 3 on top. This factor is still positive 2. This time here we're approaching 0 through negative numbers. We've got a positive on top, a negative times a positive on the bottom. So the answer is infinity because the denominator is approaching 0 and the numerator is fixed, but the sign is negative. And I mean, I'm going to erase this because we're not graphing it yet. But here, as we approach 1, our vertical asymptote at 1, as we approach 1 from the right, in this direction, the function is approaching a positive infinity. And then as we approach 1 from the left, the function's approaching a negative infinity. So that's kind of the behavior near that asymptote. And we would expect these rational functions to do something like that or something like that, but technically we don't have that information yet. All right, we do the same thing at -1, approach -1 from the left and from the right. So let me just move this. Well, I'll actually leave this and we'll just move our graph down. Oops. So similar computation, approaching -1 from the left and from the right. All right, so as we approach -1 from the right, what does the function approach? Infinity or negative infinity? So I heard both.
Negative.
So what does the top approach?
-3.
-3, because x is approaching -1. The factor x minus 1 is approaching what? -2. This factor is approaching 0, but through what values? -1 from the right of -1.
It's going to be positive.
Yeah. Does everybody agree? Positive? Just look at it this way. Here's -1. Here's 0. I'm approaching -1 through these values. Numbers that are, you know, like -1/2 or negative whatever, we're adding those to 1. Those are positive numbers. So you got a negative on the bottom. Negative times positive is negative over a negative, which is a positive. How about -1 from the left? Negative infinity. This is -3. This factor is still -2. This factor is 0, but through negative values. So you've got now a negative over a positive, which is a negative. As we approach -1 from the right, our function approaches positive infinity. And as we approach from the left, it approaches negative infinity. But notice in that middle piece, that means there's some sort of connection. We don't know exactly how it connects. You know, maybe it's something like this, maybe not, but we do know how it ends, or starts and ends, if you will. But that's the information we've gained from that. Seems kind of worthless, right? It's like you don't really get that much for all you have to do.
That's the spirit.
Huh?
Sorry, just.
I mean, and that's just how it goes sometimes. There's a lot of work to get a tiny piece of information.
We're going nowhere.
Well, we were moving, right? We were going somewhere. We're just not fully there yet. I'm gonna just leave the door open and we'll keep going until she comes in.
Get some sass if she-
Maybe she forgot today.
Come on, Allison.
Give us a reprieve. All right, so we found the domain in the vertical asymptote situation. What else can we find?
Can we find the end behavior?
The end behavior. Let's find the end behavior, or with a rational function, you either have 1 or 0 horizontal asymptote, right? So we're looking for part C. We'll say the end behavior. Yeah, we'll just say the end behavior. You just got to remember that some functions do have 2 horizontal asymptotes, but in general, how does it behave at the ends? That's where we compute our limit at infinity. Whatever our function was, x squared minus 1. Yeah, I keep forgetting. So what is the limit at infinity of 3x over x squared minus 1? 0. How do we know it's 0?
Because you just put the first 2 terms
Okay.
together and then evaluate like that.
So all we need to do at infinity for these limits is to look at the leading term divided by the leading term. And we simplify that. We see as x gets larger and larger, the quotient gets smaller and smaller. So that means we have a horizontal asymptote at y equals to 0. So we know these things are a horizontal asymptote. Any questions on that? Okay.
You would do negative infinity as well, though, right?
You can, yeah.
I know it's the same thing.
Yeah. In general, though, the end behavior on rational functions, it's the limit at infinity and negative infinity will always give you the same result because the rational functions have at most one horizontal asymptote. But in general, if you're not dealing with a rational function, specifically a polynomial over a polynomial, then yeah, you should look at the limit at infinity and negative infinity. Okay. So we've got sort of this behavior of our function taking place. We now know that way out here are functions here or our functions here, but this is where the, here or here, this is where the behavior near the vertical asymptotes tells us exactly which one of those is it. On the far left, since we know that it behaves this way near the x equal -1, we have to have this situation here, not the one above. I mean, you can cross the horizontal, but we can see that coming out too. On the far right end, it has to be this piece to connect with our green piece that we had here. But again, we'll get a clear picture of that once we determine, what's happening here, for instance, for the first derivative. Is it increasing or decreasing? And then is it concave up or concave down? Oh, yeah. Okay, so that's in behavior. Part D, we'll look at the intervals of increasing and decreasing and local mins and maxes. So then that's where we'll use the first derivative, and then we'll look at the second derivative stuff too. But we'll stop there. Does anyone have any questions? On your homework, at least for some of them, go through this process. Don't just graph it and then select A, B, C, or D. You're not going to do yourself any favors if you do that. You'll save a whole lot of time, but that's about all you'll save.
It's a hard sell.
It's a hard sell until you get your exam back and you're like, oh man, should have done it by hand.